Hello, students, and a very warm welcome to all of you. Today, we're going to dive into a really fascinating topic from your chemistry syllabus, the different types of chemical reactions. So let's get started, shall we? Now, that's a really good question, isn't it? I mean, there are literally millions of chemical reactions happening all around us, and even inside our own bodies. So how on earth do we make sense of them all? Well, think of it like this. Imagine a huge library. If all the books were just thrown into one big pile, finding the one you need would be, well, impossible. But when we organize them by subject, it becomes so much easier, right? That's exactly what we do with chemical reactions. We group them to see the patterns. So, here's our game plan for today. First, we'll talk about why we even need to classify reactions. Then, we'll dive into three major types: combination, decomposition, and displacement. And finally, we'll wrap up with a quick revision to make sure you've got it all sorted for your exams. Okay, so let's get right into it. At its core, what is a chemical reaction? It's all about breaking old bonds between atoms and making new ones. So by putting reactions into different groups, we start to see patterns. And these patterns, they're like a cheat code. They help us predict what's going to happen when we mix different things together. It makes chemistry less about just memorizing facts and much more about really understanding what's going on. All right, let's start with our first and I think the simplest type of reaction. It's called a combination reaction. And if you just remember this one simple phrase, you'll never forget it. When two become one. So, what is a combination reaction? It's exactly what it sounds like. It's when two, or maybe even more, reactants, let's call them A and B, they combine, they come together to form just one single product, C. The key thing you need to look for is that there's only one substance on the right side of that arrow. That's your big clue. Okay, let's look at a really common example of this. Imagine you're in the lab. We take a little bit of calcium oxide, you might also know it as quicklime, and we put it in a beaker. Now, we start to slowly, carefully add water to it. You know what happens? It gets quite dramatic. The mixture starts to hiss, and if you were to carefully touch the outside of the beaker, you'd feel it getting quite warm. And this is the chemical reaction that's happening right there in the beaker. We have calcium oxide, which is a solid, reacting with water, a liquid, and see what it forms? Just one single product, calcium hydroxide, which we call slaked lime. And notice that little plus heat at the end? That's really important. It shows that the reaction is releasing a lot of heat, and that's why the beaker felt so warm. You know, combination reactions are happening all around us. For example, the burning of coal. That's just carbon combining with oxygen to give a single product, carbon dioxide. What about the formation of water? Two gases, hydrogen and oxygen, combine to form one liquid, H2O. And think about this, even the breathing that you're doing right now, respiration, it's a type of combination reaction where glucose from our food reacts with the oxygen we breathe in. And that's what releases the energy that keeps us going all day. So this idea of releasing heat brings us to a very important term. Any reaction that releases heat, like our quicklime experiment, is called an exothermic reaction. It's easy to remember. Exo means exit or out, and thermic has to do with heat, so heat goes out. The burning of coal and even our own respiration are fantastic examples of exothermic reactions. All right, let's move on to our next type of reaction, decomposition. Now, this one is super easy to remember if you just think of it this way. If combination was two becoming one, well, decomposition is the exact opposite. It's one breaking apart into two or maybe even more. So let's define it properly. A decomposition reaction is when a single compound, let's call it AB, breaks down into simpler substances like A and B. So what's the big clue here? You start with just one single reactant on the left side of the arrow. But to break a compound apart, to break those chemical bonds, you need to give it some energy. It doesn't just happen on its own. And where does this energy come from? Well, it can be supplied in three main ways. We can use heat, and we call that thermal decomposition. We can use electricity, which is called electrolytic decomposition. Or we can even use light, and that's called photochemical decomposition. Let's take a look at an example for each of these one by one. First up, let's talk about using heat, thermal decomposition. In this experiment, we take these pretty green-colored crystals of ferrous sulfate, and we gently heat them in a test tube. As they get hot, you'll see two things happen. First, that lovely green color starts to change. And second, you might smell something, a very specific smell, like burning sulfur. Now remember, in the lab, always be careful. Don't put your nose right over the test tube. Just gently waft the gas towards you like this. So here's the equation that shows us what's happening. See? Our single reactant, ferrous sulfate, is breaking down into 3 simpler products. Now I want you to pay very close attention to this next part, because it's a very important tip for your exams. Do you see the word heat written above the arrow? You must always write the condition for the reaction, whether it's heat, light, or electricity. It's a very common place to lose marks, so don't forget it. Okay, next up is decomposition using electricity. This setup here shows something called the electrolysis of water. It's quite simple, really. When we pass an electric current through water, it gives the water molecules the energy they need to break apart. And what do they break into? Well, they're basic components, hydrogen gas and oxygen gas. You can actually see the bubbles of these gases forming and getting collected in those 2 test tubes. And our final type of decomposition uses light energy. It's quite amazing, actually. If you take some white silver chloride powder in a dish and just leave it out in the sunlight, you'll see a very interesting change. That pure white powder will slowly turn gray. Why does that happen? Because the sunlight is providing the energy for the silver chloride to break down or decompose into solid silver, which has that gray color, and chlorine gas. All right, on to our third major reaction type for today, displacement. The main word to focus on here is displace, which really just means to push something out of its place. The best way to think about it is like a swap. Imagine a more reactive, or you could say stronger element, comes along and it kicks a less reactive, weaker element out of its spot.
So the proper definition is this. A displacement reaction is one in which a more reactive element displaces a less reactive element from its compound. Let's look at the general form. You see we have element A and the compound BC. Now if A is more reactive than B, it will come in, push B out of the way, and form a new compound AC. And poor old B is left all on its own. It's all about who is more reactive.
Let's look at a classic experiment to really understand this. Imagine we take a shiny iron nail and we dip it into this beautiful blue solution of copper sulfate. What do you think is going to happen? Well, it all comes down to a simple question. Which is more reactive, iron or copper? As it turns out, iron is more reactive. So what's it going to do? It's going to displace the copper, pushing it right out of the solution. And if you left that nail in there for a while, you'd actually see 2 things. The shiny nail would get covered in a reddish-brown coating of copper, and that lovely blue color of the solution would start to fade. Okay, so we've covered our 3 main types of reactions. Now, let's put it all together and do a quick revision. This will be super helpful for you to remember how to identify these reactions, especially in your exams. This table here really summarizes everything beautifully. For a combination reaction, what's the key identifier? A single product. Easy. For decomposition, what do you look for? A single reactant breaking down. And for displacement, you're looking for one element swapping places with another element in a compound. If you just remember these key identifiers, you'll be able to spot the reaction type very quickly. And hey, if you want to make it even simpler, just lock these phrases into your memory. Combination, it's all about making one thing. Decomposition, that's about breaking one thing. And displacement, that's about swapping one thing. If you can remember that simple pattern, you really can't go wrong. So, you see, we've built a really strong foundation today. But in chemistry, there's always a next step, isn't there? A logical question to ask next would be, what happens when we talk about the gain and loss of oxygen during these reactions? Well, that question leads us to our next very important topic, oxidation and reduction. But we'll save that for another time. And to leave you with a final thought, remember that chemistry isn't just something you read about in a textbook. It's happening all around you right now. Is someone cooking food in your house? Is there an iron gate outside that's rusting? Take a look around and see if you can spot one of the reaction types we talked about today. Try to find one and name it. The best way to learn is to keep observing. So keep looking and keep learning. All the best.